take this lightly. I mean, anyway, let's go and recap. Trig substitution. This topic is very powerful tool, but to master it, it takes some effort to master it. Okay, so here's what we do we make a little table. I gave you this last time. I'm going to rewrite it again. You have the expression, you have the substitution, and I'm going to write next to it the domain. So this is maybe slightly different than what I gave you on Tuesday. It goes like this. We are going to look at three different expressions. The first one is the square root of a squared minus x squared. The substitution here. Notice that for this number to be a real number, x has to be less than a, or x squared has to be less than a squared. Okay, so in order to guarantee that, we can substitute x with a sine theta. Okay, because we know that sine squared of theta is less than 1, is a number between 0 and 1. So it's guaranteed that x squared is a squared sine squared theta, and the radicand remained positive, or 0. Now, in the process of using this solution, we'll have to do the inverse. We need to find the inverse of the sine if we want to solve for theta. The sine itself is not an invertible function, if you remember, because it failed the horizontal line test. So in order to overcome that and make it invertible, we confine the domain, and we say if you restrict the domain to go from negative pi over 2 to positive pi over 2, over this interval, the sine is invertible. It passes the horizontal line test. So we're going to say that theta, the domain of theta, will be greater than or equal negative pi over 2 and less than or equal positive pi over 2. We can accept negative pi over 2 and positive pi over 2, but we cannot go beyond this. The next expression we're going to deal with will be the following. What happens if we have x squared, let's see, am I going a little bit out of order? Not necessarily, it doesn't matter. Let's look at x squared minus a squared, like so. Here, we need to guarantee that x squared is greater than a squared, so the radicand will stay positive, right? A function that can produce this result, where x squared is always greater than a squared, or at least equal to, will be the secant. So if we'll substitute x with a times the secant of theta, okay, and this is a product, it's not the inverse secant, it's a times the secant. This is the secant. You don't see well. Sorry about that. Okay, but this is the secant, so now, why this works for us, secant is either greater than 1 or less than negative 1. The secant squared will be a number greater than or equal 1. So it guarantees that the radical is a real number, or the radicand, x squared minus a squared, is positive, or the least 0, but not negative. Okay, now, the secant, we have an issue with the secant when it comes to the domain. We need to have a one-to-one domain where the secant is positive. Well, that will be the first quadrant. So we're going to say that theta will be greater than 0. We can have it equal to, because secant of 0 is 1, but less than pi over 2. Because, and it's not equal to pi over 2 because the secant of pi over 2 is undefined. Remember, the secant is the reciprocal of the cosine, 1 over cosine. Cosine of pi over 2 is 0. So you end up having 1 over 0. So you cannot have theta equal pi over 2. Now we need also a one-to-one domain for a negative value. And that will be the third quadrant. So we're going to say that we're going to use this, or we're going to let theta go be greater than pi, we can have it equal pi as well, because secant of pi is -1, but less than 3 pi over 2, or 270 degrees. Okay, so the value of the secant will be negative here and positive here. So we're restricted, and now we have a invertible domain of the secant. The last one is when we have x squared plus a squared, or a squared plus x squared, like so. Now here we don't care so much about the domain, as the quantity, the radicand is always positive. But because x can be any number from -infinity to +infinity, a trigonometric function whose range is like that will be the tangent. The tangent go from -infinity to +infinity. Indeed, the substitution will be a times the tangent of theta, like so. Again, we need to think about domain of the tangent, that is where the tangent function is invertible. Well, that will be, again, -pi/2 to +pi/2, right? Except it's not inclusive, because tangent of pi/2 or tangent of -pi/2 is undefined. Again, because the cosine sits in the denominator and the cosine is 0. So we have vertical asymptote. So this is the difference between the sine and the tangent, is the inclusion of the endpoints or exclusion of the endpoints. And this is basically the table of trigonometric substitution. So it's helpful when we are dealing with expression in the integral that contain these type of radicals. Go ahead, Manny. Time for your first question. Say again? Because the tangent is not invertible. Eventually we'll have to solve for theta. Eventually. And so we cannot go from 0 to 2 pi, or from -pi to pi, because then the function is not invertible. You're going to have two values for theta. Think about that. We need to have a one-to-one function. And the tangent is one-to-one only or if you restrict the interval. Okay. When you solve for theta, you need to have only one solution. If you don't restrict the interval, you have two solutions. That's...
So it means you actually just to make it
right. That's the meaning of one-to-one. That's the meaning of invertible function. For instance, y equal x squared is not invertible. It's not one-to-one because x equals plus or minus square root of y. So we need to restrict. We're going to say y equal x squared, square root of x. I'm sorry, y equal x squared is invertible if it goes 0 to infinity. But it's not invertible if you go -infinity to infinity. All right. Let's get to work here, because this is just a warm-up, preliminary stuff.